Here's something that will blow your mind. If you could count every star in our galaxy alone, you'd reach 400 billion before you even started on the roughly 2 trillion other galaxies scattered across the observable universe. Current estimates place the total number of stars at around 200 billion trillion throughout all of space. With all those blazing suns radiating light in every direction, logic says the night sky should be as bright as daylight. Yet when you look up at night, you see mostly darkness. This contradiction stumped astronomers for over 400 years until recent discoveries from the James Webb Space Telescope finally revealed the shocking truth about why our universe remains dark. The fundamental mystery that stumped scientists. This contradiction forms the foundation of what astronomers call Olbers Paradox, named after Heinrich Olbers, who formalized the problem in 1823. The mathematical logic appears unbreakable. If the universe extends infinitely in all directions and contains a uniform distribution of stars, then every line of sight from Earth should eventually intersect with the stellar surface. This means the entire night sky should glow with the combined brightness of all those stellar surfaces, creating a luminosity comparable to staring directly at the sun's photosphere. Johannes Kepler first recognized this astronomical puzzle in the early 1600s when he observed that the darkness of night seemed to contradict the infinite universe model that many scholars accepted. Kepler reasoned that if space truly contained endless stars stretching to infinity, the accumulated light from all those distant suns should make nighttime as brilliant as day. The fact that darkness dominated the night sky led Kepler to conclude that the universe must have boundaries, with a finite number of stars distributed across a limited volume of space. Yet Kepler's finite universe solution created its own problems. If stars existed only within a bounded region of space, what lay beyond those boundaries? The concept of an edge to the universe raised uncomfortable questions about what might exist in the void beyond the stellar realm. These philosophical implications troubled scientists who preferred elegant, unbounded cosmic models that avoided arbitrary limits on the universe's extent. The paradox gained renewed attention during the 19th century as telescopes revealed ever more distant stars and nebulae. Each improvement in observational technology uncovered additional layers of cosmic structure, suggesting that the universe contained far more luminous objects than previously imagined. Heinrich Olbers approached the problem with mathematical rigor, demonstrating that even accounting for the inverse square law of light intensity, an infinite universe with uniformly distributed stars would still produce a blindingly bright night sky. Olbers calculated that while individual distant stars contribute less light due to their remoteness, the sheer number of stars at each distant shell would compensate for this dimming effect. In an infinite universe, the number of stars within successive spherical shells increases as the square of the radius, exactly canceling out the inverse square reduction in brightness from each individual star. This mathematical relationship meant that stars at every distance would contribute equally to the total sky brightness, making the darkness of night theoretically impossible. Several 19th century scientists proposed solutions involving interstellar dust that might absorb starlight before it reached Earth. They suggested that cosmic dust clouds scattered throughout space could block the light from distant stars, explaining why the night sky remained dark despite containing countless luminous objects. However, this dust absorption hypothesis contained a fatal flaw. Any material capable of absorbing enough starlight to darken the night sky would eventually heat up and begin glowing itself, ultimately contributing its own thermal radiation to the cosmic brightness. The paradox challenged fundamental assumptions about the nature of space, time, and cosmic structure. If the universe truly extended infinitely and had existed for an infinite duration, then light from every possible stellar source should have had sufficient time to reach Earth. The mathematics suggested that under these conditions, the night sky should shine with an intensity of approximately 200,000 times brighter than the full moon, creating perpetual daylight conditions across Earth's surface. Early 20th century astronomers began recognizing that the darkness paradox might reveal something profound about cosmic evolution and structure. The problem forced scientists to question whether their basic assumptions about the universe's properties might be fundamentally incorrect. Perhaps the universe was not infinite in extent, or maybe it had not existed for an infinite duration, or possibly the distribution of stars was not as uniform as previously assumed. The stakes of solving this paradox extended far beyond academic curiosity. The darkness of night touched on fundamental questions about the origin, evolution, and ultimate fate of the universe itself. If scientists could understand why space appeared dark, despite containing enormous numbers of luminous objects, they might unlock secrets about the cosmic timeline, the universe's geometry, and the physical laws governing light propagation across vast distances. The paradox also connects to everyday human experience in profound ways. Every person who has ever looked up at a star-filled night has witnessed this cosmic mystery firsthand. The sense of awe and wonder that darkness evokes stems partly from the subconscious recognition that something about the night sky defies our intuitive expectations. Our brains evolved to associate brightness with safety and darkness with potential danger, making the cosmic darkness feel both beautiful and slightly unsettling. Current research suggests that solving Olbers Paradox requires understanding multiple interconnected phenomena that were unknown to 19th century astronomers. The expansion of space itself affects how light propagates across cosmic distances, while the finite age of the universe limits how much light has had time to reach any given observation point. Additionally, the universe's structure is far from uniform, with matter concentrated into galaxies and galaxy clusters separated by vast empty regions. The paradox ultimately revealed that the universe possesses a hidden architecture that completely contradicts our intuitive assumptions about cosmic brightness. To understand why this cosmic darkness persists, we need to examine how light behaves in our own immediate environment and compare it to the vast emptiness of space. How Earth creates its brilliant daylight. Consider how Earth transforms a single star's light into the brilliant daylight that illuminates our world from horizon to horizon. The sun represents just one ordinary star among the countless billions scattered throughout the galaxy, yet during daytime hours it manages to flood our entire planet with radiant brightness. This remarkable transformation occurs not because our star possesses any special properties compared to distant suns, but because Earth possesses something that space completely lacks, an atmosphere packed with particles that redirect and amplify the incoming solar radiation. Our atmosphere contains approximately 78% nitrogen, 21% oxygen, and traces of other gases, along with countless microscopic particles including dust, water droplets, and aerosols suspended throughout the air column. These components create a dense medium that fundamentally alters how light behaves when it enters our atmospheric envelope. Every photon arriving from the sun encounters billions of these tiny obstacles during its journey through the air, causing the light to bounce and scatter in multiple directions rather than traveling in straight lines. Rayleigh scattering governs this atmospheric light redirection process. When sunlight encounters gas molecules and particles smaller than the wavelength of visible light, these tiny objects act as microscopic mirrors that deflect the incoming radiation. The effectiveness of this scattering depends directly on the wavelength of the light involved. Shorter wavelengths experience much stronger scattering than longer wavelengths, with blue light scattered approximately 10 times more effectively than red light. This wavelength-dependent scattering explains why our daytime sky appears blue rather than the white color of direct sunlight. Blue photons with wavelengths around 450 nanometers get bounced around the atmosphere so extensively that they seem to arrive from every direction simultaneously. Meanwhile, red photons with wavelengths near 650 nanometers pass through the atmosphere with minimal deflection, allowing them to maintain their original directional properties. The result creates the familiar blue dome that surrounds us during daylight hours. The atmosphere essentially functions as a vast network of light redistributors. Each gas molecule and particle acts as a tiny relay station that captures incoming solar radiation and broadcasts it in random directions. This process transforms the sun's parallel beam of light into a diffuse glow that illuminates the entire sky hemisphere. Without this scattering mechanism, we would see only a brilliant white disk of the sun against a completely black background, similar to what astronauts observe from space. Atmospheric particles redirect light with remarkable efficiency. A single photon might encounter hundreds of scattering events during its passage through the air column, getting bounced from molecule to molecule before finally reaching our eyes. This multiple scattering creates the soft, even illumination that characterizes terrestrial daylight. The light arriving at any location on Earth's surface includes both direct radiation from the sun and scattered radiation from all other directions, combining to produce the bright conditions we experience. The thickness of our atmospheric layer determines how extensively this scattering occurs. During midday, when the sun reaches its highest position, sunlight travels through the minimum amount of atmosphere, resulting in intense blue sky conditions. As the sun approaches the horizon during sunrise and sunset, light must traverse increasingly thick atmospheric layers. This extended path allows more scattering opportunities, causing shorter wavelengths to get deflected away while longer red and orange wavelengths continue toward the observer. Astronauts orbiting Earth witness a dramatically different visual environment that reveals how unusual our atmospheric light amplification really is. From space, the sun appears as an intensely bright point source against the absolute blackness of the cosmic void. Even with the sun shining directly on their spacecraft, astronauts see no diffuse sky glow whatsoever. The absence of atmospheric particles means that light travels in perfectly straight lines, creating stark contrasts between illuminated and shadowed regions. This atmospheric amplification effect theoretically should apply to starlight as well as sunlight. Every star in the night sky emits photons that enter our atmosphere and encounter the same gas molecules and particles that scatter solar radiation. The light from Sirius, Vega, and countless other stars should undergo Rayleigh scattering, just like sunlight does, creating diffuse glows that brighten the night sky. Yet, despite containing the same scattering mechanisms that create brilliant daylight, our atmosphere fails to transform starlight into significant sky brightness. Even on the clearest nights, far from artificial illumination, the scattered starlight contributes only a faint glow that remains barely detectable to human vision. This dramatic difference between the atmosphere's treatment of sunlight versus starlight hints at fundamental distinctions between our local star and the distant stellar population. The intensity difference between sunlight and starlight provides the crucial factor explaining this atmospheric amplification discrepancy. Our sun delivers approximately 1,360 watts of energy per square meter to Earth's upper atmosphere, creating an enormous flux of photons available for scattering. In contrast, even the brightest stars deliver less than 1/1,000,000th of this energy flux, providing far fewer photons for the atmospheric scattering process to redistribute. Our protective atmospheric envelope creates a localized bubble of enhanced brightness around Earth by capturing and redistributing the intense radiation from our nearby star. This process transforms what would otherwise be a single brilliant point of light into the diffuse, comfortable illumination that sustains life on our planet. However, this same atmosphere cannot perform similar brightening magic with the incredibly faint light arriving from distant stars scattered throughout space. The brilliant blue sky that surrounds us represents an artificial enhancement created by our planet's gaseous envelope, but this raises a profound question about what happens to light when it encounters the vast emptiness between the stars. The shocking emptiness of space. Space operates under completely different rules than our familiar atmospheric environment. The vacuum between stars contains fewer than 1 atom per cubic centimeter, creating conditions so empty that light rays travel for billions of years without encountering a single particle capable of redirecting their path. This extreme emptiness fundamentally changes how illumination behaves compared to the dense conditions that create Earth's bright daylight. The interstellar medium represents the closest thing to a perfect vacuum that exists in nature. Between stellar regions, particle density drops to levels that terrestrial laboratories struggle to replicate even with advanced vacuum technology. A cubic meter of space might contain fewer particles than exist in a single breath of Earth's atmosphere. This sparse distribution means that starlight encounters virtually no obstacles during its passage through the cosmic environment. Without scattering particles, light maintains its original directional properties throughout its journey across space. Photons travel in perfectly straight lines from their stellar sources without experiencing the random deflections that create atmospheric brightness on Earth. Each light ray maintains its precise trajectory, carrying energy in a narrow beam that only becomes visible when it directly enters an observer's eye or strikes a physical surface. The space between these light beams remains completely dark because no particles exist to redirect the energy toward other viewing angles. This directional nature of unscattered light explains why astronauts see only pinpoints of stellar brightness against an otherwise black background. Even when surrounded by intense starlight streaming in all directions, the space around them appears dark because their eyes detect only the photons traveling directly toward them. The countless light rays passing nearby remain invisible because nothing deflects them into the astronaut's line of sight. The contrast between Earth's atmospheric density and space's emptiness becomes apparent when comparing their particle concentrations. Our planet's atmosphere contains approximately 2.5 quintillion molecules per cubic centimeter at sea level, creating a dense medium that interacts extensively with incoming radiation. The interstellar medium averages less than 1 particle per cubic centimeter across most of its volume. This represents a density difference of more than 24 orders of magnitude, explaining why atmospheric scattering creates bright skies while space remains dark. Even regions that astronomers consider relatively dense still contain far too few particles to generate significant light scattering. The densest molecular clouds in the galaxy might reach concentrations of several million particles per cubic centimeter, which sounds impressive until compared to atmospheric densities. These supposedly dense cosmic regions still contain fewer particles than exist in the best laboratory vacuums on Earth, making them incapable of producing the scattering effects that brighten terrestrial skies. The concept that darkness represents the absence of scattering rather than the absence of light fundamentally changes how we understand cosmic illumination. Space contains enormous quantities of electromagnetic radiation streaming in all directions from countless stellar sources. This energy fills the cosmic volume, carrying power levels that would overwhelm any observer if concentrated into visible form. However, without particles to redirect and scatter this radiation, it remains invisible to anyone not positioned directly in its path. Consider the light streaming past Earth from distant galaxies at this very moment. Trillions of photons carry energy through the space around our planet, traveling on trajectories that will carry them to other regions of the universe. These light rays pass invisibly through the solar system because no scattering medium exists to make them visible. Only the tiny fraction of cosmic light that happens to travel directly toward Earth becomes detectable, while the vast majority continues its journey unseen through the empty space between celestial objects. This explains why adding more stars to the universe cannot solve the darkness problem through simple multiplication. Each additional star contributes its own beam of directed light, but these beams travel in straight lines without illuminating the space between them. 1 trillion stars produce 1 trillion separate light beams, but the dark regions between those beams remain just as dark as before. The emptiness of space ensures that increased stellar populations create more points of light rather than diffuse cosmic brightness. Cosmic dust plays a particularly important role in the limited scattering that does occur in space. These microscopic solid particles, composed primarily of silicates and carbon compounds, interact more effectively with light than individual gas molecules. Dust grains can absorb starlight and re-emit it at longer wavelengths, creating the faint infrared glow that space telescopes detect throughout the galaxy. Yet even in dust-rich regions of space, the particle density remains far too low to generate the bright, scattering effects that characterize planetary atmospheres. The straight-line propagation of light through empty space also means that stellar illumination decreases rapidly with distance from each source. Unlike atmospheric scattering that distributes light evenly across the sky, cosmic illumination follows strict geometric relationships that determine how much light reaches any given location. The mathematical precision of these distance relationships reveals another crucial factor that contributes to cosmic darkness: the mind-bending scale of stellar distances. These distance relationships become staggering when we examine our cosmic neighborhood in detail. Our nearest stellar neighbor beyond the Sun lies so far away that traveling there with our fastest current spacecraft would require more than 70,000 years of continuous flight. Proxima Centauri sits at a distance of 4.246 light-years from Earth, which translates to roughly 25 trillion miles of empty space, separating us from the closest star we could theoretically visit. This immense gap represents just the beginning of understanding how cosmic distances create the darkness that surrounds us each night. Within a sphere extending 50 light-years from our solar system, astronomers have cataloged approximately 2,000 individual stars. This count might seem substantial until you consider the volume of space involved. That sphere contains roughly 65,000 cubic light-years of mostly empty void, meaning each star occupies an average volume equivalent to about 32 cubic light-years of space around it. These measurements demonstrate that stars exist as isolated islands of light floating in an ocean of darkness. The average distance between neighboring stars and our galactic neighborhood measures approximately 5 light-years, though this spacing varies considerably in different regions. Some stellar pairs orbit much closer together, while vast stretches of space contain no stars whatsoever across distances spanning dozens of light-years. The overall pattern creates a three-dimensional network where bright points remain separated by enormous volumes of empty darkness. Light intensity follows the inverse square law with ruthless mathematical precision as it travels through these cosmic distances. When starlight spreads outward from its source, the energy disperses across increasingly larger spheres of space. A star located twice as far away delivers only 1/4 the light intensity to any observer. At 10 times the distance, the same star appears 100 times dimmer. This relationship means that even massive, luminous stars become nearly invisible when viewed across the typical distances that separate stellar objects. Consider Rigel, one of the most luminous stars visible in Earth's night sky. This blue supergiant generates approximately 120,000 times more light than our Sun, making it one of the most powerful stellar engines in our local galactic region. Yet Rigel appears as merely a bright dot to the naked eye because it lies roughly 860 light-years away. The inverse square law has reduced its tremendous luminosity to a tiny fraction of its original intensity by the time that light reaches Earth. If Rigel occupied the same position as our Sun, it would incinerate our planet with its overwhelming energy output. The mathematical relationship governing stellar brightness across cosmic distances ensures that only a handful of nearby stars contribute meaningful illumination to Earth's night sky. Stars beyond approximately 100 light-years become so dim that they blend in hard general background glow, regardless of their actual luminosity. Even if astronomers discovered a star 1 million times brighter than our Sun, placing it at a distance of 1,000 light-years would render it barely visible to human vision due to the relentless effects of distance dimming. These vast separations create enormous regions of space that receive virtually no starlight whatsoever. The darkness between stellar systems extends across light-years of empty void where no significant illumination exists to brighten the cosmic environment. Spacecraft traveling through interstellar space would experience conditions of almost perfect darkness, with only the faintest pinpricks of distant stars providing any visual reference points.